and get in your final answer to the clicker question. For those of you just walking in now, you might not have a chance to get all of the thought process that you need in on this clicker question because it is based on a Lewis structure, so we will go over it. But for those of you that have been here for 30 seconds or longer, see if you can get the right answer in here. All right, so, okay, it looks like we have a very mixed response in terms of the answer to the clicker question today. Raise your hand if you didn't have time to figure out the Lewis structure. Okay, so that accounts for some of you. Let's go over the correct answer to this question. So who got the right answer? 31% of us. This is not the kind of percentages we're looking for, so let's go over this. In class on Monday, we did go over the geometries, and the geometries themselves are very straightforward once you know what the Lewis structure is. But remember, you can't just always look at a molecule and automatically know the Lewis structure. We actually need to think about those valence electrons. So here we're dealing with selenium hydride, so SeH2. I told you that there's 6 valence electrons in selenium, so we have 6 there, plus 1 for each of the hydrogen. So what we should have is 8 valence electrons in our Lewis structure. How many electrons do we need to have full valence shells? 12, that's right. We need 8 plus 4 is 12 for full shells. That means that we need 12, excuse me, yes, that means that we need 12 minus 8, or 4 bonding electrons in our structure. So I tried to give you one that you could draw pretty quickly. It just has hydrogens in it. So we have SeH2. We can do our 4 bonding electrons. How many valence electrons do we have left? 4. That's right. So we need to fill our octet for selenium. So 1, 2, 3, 4. So this is our Lewis structure here. Hopefully you can see why it's not linear. If it were linear, which 32% of you seem to have thought, that would have meant that our Lewis structure had no lone pairs in it, right? And that's not the case. We have 2 lone pairs. So if we thought about what the bonds were everywhere, it would be 109.5. But it's bent because we're only looking at the bonds. We're not counting the Lewis structures in naming our geometry, but they do affect the angles. And it turns out that it's actually less than 109.5 because those lone pairs are pushing the bonds even further away.